While studying the hydroplate theory in the Grand Canyon, a common sedimentary deposit on Earth's surface comes up time and again. The standard explanations for the origin of limestone are very different from that of hydroplate theory. Other theories propose that limestone formed at Earth's surface, as part of Earth's biosphere, where all life is contained. However, the standard theories for limestone formation suffer from the following problems. The chemistry behind the accepted models for limestone formation would make the atmosphere and oceans toxic hundreds of times over. The standard models require hundreds of shallow seabeds to sink, each of them, at just so rates for millions of years to achieve the layer thicknesses that are observed. Standard models do not address where inexplicably enormous quantities of raw materials come from to produce so much limestone. The claimed super-slow formation of limestone requires large buried fossils like nautiloids to lay exposed for thousands of years during burial without signs of damage or erosion in the final fossil. Many nautiloids are formed in a vertical orientation within the limestone deposits. This compounds the problem of slow limestone formation, as it would take even longer to bury the exposed original material before it then began to fossilize. A formation model also has to explain how limestone, which forms in liquid water, ends up in comets and asteroids. Standard limestone models do not address these problems. A workable geologic model should be able to provide a scientifically grounded, cause-to-effect explanation that directly addresses these issues. Those who have watched my other videos will see how the last two issues are readily addressed and uniquely answered by hydroplate theory. Feel free to watch the hydroplate overview series of videos parts 1, 2, and 3, and the origin of comets and asteroids video to discover hydroplate theory's answers for these last two items in more detail. This video will highlight the remaining problems for standard limestone formation theories and show hydroplate theory's simple yet detailed solutions to these otherwise difficult problems. Limestone is estimated to make up 20% of all of Earth's sedimentary layers, so that means there's roughly 40 million cubic miles of limestone on Earth. As hydroplate theory shows, the flood's initial ejection of large amounts of materials far from Earth explains why calcium carbonate, which only forms in liquid water, is found in cold comets, asteroids, and meteorites. As the flood progressed, this thick blanket of calcium carbonate was distributed by the floodwaters in the sediments and became the cementing agent which formed thick layers of limestone spread over vast areas of all continents. But limestone's chemical makeup reveals even more about why it had to have originated below Earth's surface. For clarity, it is important to understand the scope of material being included when we speak of limestone. In this discussion, limestone is used broadly and includes many varieties of calcium carbonate deposits whose common names are listed here. Many of these limestone deposits are exceedingly thick and pure, covering vast swaths of Earth's surface. For example, the exposed Redwall limestone averages 400 feet thick and covers a great deal of northern Arizona. An even thicker deposit rests off the coast of Florida and Cuba, covering 200,000 square miles of area, and is thought to extend in places as deep as 6 miles down. Standard explanation for most deposits like these is that they formed on Earth's surface in shallow seas over eons of time. In the origin of the Grand Canyon video, we've already covered some of the fundamental problems with this scenario of stratification of layers, which requires multiple appeals to just so conditions. But let's discuss a bit further why limestone is believed to have been generated in warm, shallow seas. For example, if you look up limestone at geology.com, you will be told that most limestone forms underwater from biological organisms like coral and other shell or skeletal producing fauna, which are able to extract the dissolved minerals from the ocean water to produce calcium carbonate shells and structures which after death are pulverized and slowly collect over time, building up on the ocean floor and eventually turning into rock. Geologists know that under the right conditions, limestone can precipitate directly from the seawater as well. Over millions of years, it is believed that a thick deposit of limestone forms into something like the Redwall limestone layer as seen in the Grand Canyon. This is why it is said that that area of the Grand Canyon was once a warm, shallow sea, which came and went, producing several thick limestone layers at different levels before the canyon formed, and long before it was lifted over a mile above sea level by the Colorado Plateau. The Bahamas Bank, or platform, is given as a current example of an active limestone forming environment. But let's consider this fine-tuned scenario for limestone formation. The reason warm, shallow seas are nearly always proposed to explain these thick limestone deposits is because of the assumption that most limestone originates as a result of biological organisms that generate it in the production of coral, shells, and skeletal structures. However, these organisms cannot survive without sunlight or if temperatures are too cold. Much of the Bahamas platform, for example, is often less than 30 feet below sea level. Coral growth becomes poor below 60 feet and cannot grow at all much below 300 feet. Therefore, very thick deposits of limestone must have formed in warm, shallow seas. But consider what a careful just so balance of multiple variables is required for this scenario to play out. For a thick layer to form, the seafloor must drop away by some undefined yet fine-tuned mechanism. This undefined dropping of the seafloor must occur at a precise and even rate over millions of years. If it drops too slowly during that time, then the limestone will build up too fast and the sea will dry out before the thick layer can develop. If the floor drops too quickly, the organisms producing the limestone will die. Remember, too, that the organisms can't just make their shells and structures out of nothing. They require source materials in solution with the seawater. Where did that come from? In all cases, a viable source of the required building blocks of aqueous calcium and bicarbonate ions dissolved in the sea's water must also be identified in sufficient amount to explain the enormous mass of limestone that's been produced. Remember, the Bahamas bank is up to 6 miles thick in places. What mechanism dropped the seafloor at such even rates to build up miles-thick layers of organic limestone deposit? What was the continuous source of dissolved minerals to support limestone growth while not choking out other sea life? Few consider, much less attempt to answer these difficult yet important questions if the warm, shallow sea concept is to be believed. However, even these fine-tuning issues for the warm, shallow sea are minor compared to the tremendous problem that limestone's chemical formation presents. Any theory claiming these large deposits of limestone were generated on Earth's surface and in Earth's biosphere must face the carbon problem. As we'll see, this problem exists whether one accepts that the limestone has an organic origin or is the result of chemical precipitation as either a sea or a large lake evaporate. Remember, limestone is calcium carbonate. Each molecule of limestone contains one carbon atom. When looking at the distribution of carbon on Earth, we find that the amount of carbon locked into limestone is extremely lopsided. In fact, if we take all the carbon in Earth's atmosphere, which contains carbon dioxide and carbon monoxide, plus all life forms living and dead, which of course are all carbon-based, plus all coal and oil deposits, which are the remains of past carbon-based life, plus the huge amount of dissolved carbon in Earth's oceans, all of this combined is less than 1/1000th of the carbon that is locked into Earth's sedimentary limestone. Remember this immense scale of this carbon distribution problem as we now review the chemical reaction that is required in order to produce limestone. Limestone is a precipitate, or solid, from the following reversible chemical reaction. When carbon dioxide is dissolved in liquid water under pressure, it forms a weak acidic compound called carbonic acid. This chemical reaction between carbon dioxide and water is also reversible. Whenever you open a carbonated beverage, you see the result of the reverse of this reaction, where aqueous carbonic acid in the container, once under pressure, suddenly fizzes, reversing the reaction, and CO2 gas escapes into the atmosphere. When the carbonic acid solution comes into contact with solid limestone, that is calcium carbonate, the carbonic acid dissolves the limestone, forming an aqueous solution of calcium and bicarbonate ions. As stated, this reaction is completely reversible. Under the right conditions, solid limestone particles will precipitate out of solution, and in turn, the carbonic acid solution produced can revert back into liquid water and gaseous carbon dioxide. We think little of this secondary reaction producing carbon dioxide gas while enjoying a soda pop, but let's stop and think about the massive scale of limestone we just discussed. Chemistry shows us that for every carbon atom that is locked in each molecule of limestone that ever precipitated, another corresponding carbon atom must have been released as carbonic acid. If precipitation of limestone occurred on Earth's surface in warm, shallow seas, as is so popularly thought, then in this environment the oceans and atmosphere would have become toxic hundreds of times over. So how in the world could so much limestone be produced on Earth's surface without an equally massive amount of carbon dioxide choking out all life? Something is very wrong with the story that all this limestone was produced in the way that many geologists claim. Let's look again at hydroplate theory's explanation of limestone's origin and see if it can resolve the lopsided carbon problem. Remember, hydroplate theory shows how Earth's pre-flood condition was very different than what we know today, with large ocean basins and separated granitic continents. Before the Genesis flood, Earth's granitic surface was a continuous crust which trapped a deep layer of water. This was a global condition wherein the Earth crust was an unbroken spherical supercontinent of granitic rock which covered and sealed in this deep layer of water. Of course, there is much to discuss concerning the structure of this granite shell, but we won't cover that here. Those desiring more detail on this condition may learn more about the features of the pre-flood Earth in the hydroplate overview series of videos. The point to notice here in this discussion on limestone's origin is that at least half of the water in our ocean basins today started out isolated from the surface, being sealed underneath this global supercontinent shell, which was about 60 miles thick. The water under the crust was in a physical state called the supercritical state. Supercritical fluids are studied today mainly for their great potential for dissolving minerals. The greatly increased energy of supercritical fluid molecules impacting against a solid will dissolve certain minerals very effectively. Centuries before the flood, supercritical water dissolved many mineral solids from the granite crust and mantle rock, creating porous openings in the surfaces above and below the subterranean chamber. Both lab experiments and simulations show that supercritical water will precipitate, or outsalt, dissolved minerals as temperatures rise. So these minerals, including limestone, eventually precipitated out of solution and blanketed the chamber floors of the Great Deep. Now let's look at how hydroplate theory uniquely and simply explains the massive and thankfully missing carbon dioxide problem that exists for all other theories attempting to explain limestone formation as having occurred on Earth's surface. The key is understanding that the precipitation of most of Earth's limestone was not organic in nature but chemical and did not occur on Earth's surface. Rather, it occurred deep down in the supercritical waters of what the Bible calls the Great Deep. So before the flood, sealed far below Earth's surface, supercritical water dissolved many minerals from granite as temperatures rose in the subterranean chamber. These minerals were broken down into more basic molecules, elements and ions of sodium, chlorine, carbon, calcium, copper, oxygen, aluminum, magnesium, and iron were all dissolved in solution with supercritical water. In this state, new compounds could form like sodium chloride, or what we know as table salt, and aqueous calcium and bicarbonate ions. All these compounds were dissolved in solution with supercritical water. As temperatures in the subterranean chamber continued to rise, the supercritical water outsalted, producing new precipitates as various chemical reactions dictated. In the case of limestone precipitate, aqueous calcium and bicarbonate ions followed our well-known chemical reaction for limestone. As before, each of the two bicarbonate ions that reacted with calcium carried a carbon atom. Each of these carbon atoms ended up in two new yet different molecules as they chemically reacted. One of the carbon atoms produced solid calcium carbonate or limestone precipitate, which fell on the chamber floor. The other carbon atom produced aqueous carbonic acid, which remember would break down into water and CO2, especially in the high energy environment of the subterranean chamber. However, because the solution was trapped and sealed deep under the crust, this new carbon dioxide molecule could not escape up into Earth's atmosphere. Therefore, hydroplate theory solves the huge question of why Earth has over 1,000 times more limestone than it does carbon dioxide. Since the CO2 produced during precipitation of limestone could not escape, it simply dissolved back into solution with the supercritical water. Of course, this CO2 itself was in a supercritical state within the confines of the chamber, so it too aided in further dissolving of the granite and mantle materials that made up the chamber's ceiling and floor respectively. As with supercritical water, each carbon dioxide molecule produced stood a good chance of being further broken up into ions. In these conditions, eventually the components of any CO2 produced would themselves combine with stray hydrogen and oxygen ions, which were in abundance, and form yet another bicarbonate ion. This new ion then became source material for yet another limestone reaction. Rather than escaping, The extra carbon was used over and over again to dissolve more and more material and produce more and more limestone. Each cycle produced more and more limestone precipitate on the chamber floor. With each cycle, the percentage of carbon locked in limestone increased and became more and more lopsided. Thus, in this contained environment that hydroplate theory presents, we see a straightforward solution to what at first seemed like a huge mystery of missing carbon when thinking of limestone formation as occurring on Earth's surface. Hydroplate theory provides the solution explaining how vast amounts of limestone was produced and deposited while at the same time very little CO2 was generated in the process. In the initial weeks of the flood, pressure in the supercritical water dropped as it escaped the confines of the deep. Some limestone was ejected completely from Earth along with rocks and many other sediments and minerals that would eventually form into asteroids, comets, and TNOs. This explains why limestone, a substance that forms in liquid water, is consistently found in the deep frozen makeup of asteroids and comets. As the flood progressed and the fountains stopped ejecting material, enormous amounts of limestone, salts, and other sediments, which had outsalted onto the chamber floor long before the flood began, were swept up to Earth's surface. As pressure and temperature dropped in this mineral-rich slurry coming up from below, still more limestone precipitated again out of solution. As required by the precipitation reaction, carbon dioxide was once again produced, but now the carbon dioxide was not trapped and was free to disperse into Earth's atmosphere, oceans, and surface sediments. Once on the surface, as the flood continued, the process of liquefaction sorted limestone particles into thick, pure layers which we see today in the many strata covering vast areas. This sudden yet temporary increase of carbon dioxide into Earth's biosphere would provide the necessary food for vegetation to readily grow and quickly replenish the Earth after the flood. As we've just seen with limestone, the hydroplate theory readily explains how so much limestone formed without poisoning the oceans and atmosphere in CO2, how limestone formed chemically while isolated from Earth's surface, eliminating the standard theory's requirements for perfectly timed sinking of hundreds of shallow seabeds on Earth's surface, how the raw materials to make so much limestone came from granite, and how millions of well-preserved fossils like nautiloids were caught and rapidly encased in limestone. And finally, it explains how limestone ended up on comets and asteroids. Walt Brown's hydroplate theory answers many other seemingly intractable geology problems. These include physics-based cause-to-effect formation of the globe-encircling mid-oceanic ridge, the north-south orientation of major mountain ranges, overthrusts, plateaus, and ocean trenches, as well as a much better explanation for the jigsaw fit of continents, not to each other, but to the Earth's mid-oceanic ridge. Discussion of the entire theory can be freely reviewed at creationscience.com, or hit subscribe to see a full list of hydroplate theory videos that are available, and be notified of new videos.